Good afternoon, everyone. My name is Amro Farid. I'm an associate professor of engineering here at the Thayer School of Engineering. Welcome to this talk as part of our Great Issues in Energy Symposium. I'm going to be talking to you about New England's evolving electricity landscape, drawing on highlights from our ISO New England Renewable Energy Integration Study that we finished last year. At the risk of being a talking head, we're going to change things up a bit today and do a round-robin style of presentation, and having all of the team, the participants of this study, all give different parts of the presentation. And so I'd like to take a moment to introduce everyone. Zachary Berzola is a BE student here at Thayer. He was in the 3-2 program with Middlebury. So before your BE here, you'd also did physics and minor in computer science. Dakota Thompson was also in the 3-2 program with Colby, physics major in computer science minor, before asking for more, and is now a master's student within the lab. Steffi also asked for more, Steffi Mohanji. She was also a 3-2 student, Vassar, physics major, computer science minor, then BE, and is now in the third year of her PhD. And Armazd is wrapping up his doctorate within the lab. He was the lead software developer for all the simulations that we're going to be talking about today. So let me tell you a little bit about our lab. The LINES, the Laboratory for Intelligent Integrated Networks of Engineering Systems, is really concerned with some sort of physical, large-scale network of some kind, and several different layers of planning and operations control and decision-making on top of that. And if that's not all, what we really would like to do is integrate it with another physical system and other layers of planning, operations, and control. And that has led to 5 different research themes that we tend to work on. I'll be talking today about basically the smart power grids area, but we've also worked in energy-water nexus, electrified transportation, industrial energy management, and interdependent smart city infrastructures. So our goal today is to highlight results from the ISO New England Renewable Energy Integration Study. And I'm going to cover basically we're going to cover 5 different topics, a bit of introduction, and then background into how our electric power system works and what does it mean for the integration of variable renewable energy. Then we'll talk about our grid here in New England, and then the study results, and then finally bring the presentation to a close with conclusions and final insights. I'm not a man of extremes. I prefer moderation. Okay. Great. Thank you. Perfect. So every about 7 to 10 years or so, independent system operators like ISO New England will conduct some form of renewable energy integration study. And ISO New England did their last one in 2011 with GE Consulting and NREL. And what they try and look at is changes in the generation portfolio and also the changes in the transmission system. The methodologies for these studies have been evolving, and it's an area of that we've been working on, and certainly Armazd has made it the subject of his doctorate. And so we were very fortunate and grateful to ISO New England to choose us to do this particular study, because it doesn't really happen all the time. When we talk about an independent system operator, we have to recognize that they have 3 important roles. One is really from a reliability of grid operation perspective and to coordinate the flow of electricity over the region's high voltage or transmission system. They're also the market administrator. So we're going to see in a minute that not only are flows of electricity involved in our electric power system, but obviously flows of money as well, and that there's a good amount of administration. When we talk about this particular study, it's important to recognize that ISO New England's turnover is around $8 billion a year. So this is not really a small endeavor. And then finally, ISO New England has a certain responsibility to maintain the reliability not just in the now, but also into the future. And so they conduct planning studies of different types, and this is one of them. Renewable energy integration studies are particularly interesting because they have a really nice mix of energy technologies, economics, and policy. So let me turn it over to Zach.
So what does this power system actually look like? And for the last 100 years or more, it's looked like this. You have generation stations which are producing power. They're stepping up that electricity to high voltage for transmission across long-distance power lines. This reduces losses. Then, when you get to a neighborhood you'll step down the voltage to distribution system that will go out to your house or to the college. And in general, this is a one-way flow. And our study focuses from here backwards, generation and transmission. So in addition to the physical power flows, there's also monetary flows in this system. These include basically an end user who's paying for their electricity to a utility. Then that utility has to pay the generation companies. They have to pay the transmission and distribution companies that all help get that power to the end user. And this is where ISO New England comes in. They're a market facilitator helping to get from the utility back to the generation stations. And this is kind of the key piece here that we're really trying to get into. And so you might ask, who cares about this? Why is this important? And the key is there's a lot of people that care about this, even in New England, right? It's utility companies. It's the transmission and distribution system owners that own the wires that transmit the power. It's the regulators that in each state that set rules about how much power can be produced or how it can be moved around. The generation companies that actually produce the power. Energy service companies, these are people that work with buildings to improve efficiency or provide demand response, as well as environmental groups that might work with regulators and with the utilities to produce renewable portfolio standards that require certain amounts of renewable generation in each state. And the key is that all of these stakeholders help define the scope, scenario, and assumptions that went into this study. And Steffi will talk to you about how these are affecting as renewable penetrations increase going forward.
Thank you, Zach. So as the penetration of As the penetration of renewable energy resources grows, we find that the electricity grid, the way it's managed and controlled, also has to change. So as Zach mentioned, in the past, you would have a few thermal generation units which would be very well controlled and they can be dispatched to meet the demand. However, as you add more solar and wind, this dispatchability of the electricity generation becomes way diminished because suddenly you cannot decide when the sun should shine or where the cloud should be or how much wind is blowing. And so in a sense, with solar and wind generation, you get what you get. So because of this, we need new control levers that will help us manage the electricity grid, ensure that its reliability, and that's why demand-side management is seen as one of such control levers that can be used. So usually an ISO would acquire the forecast for the net load, and so where the net load is the difference between the actual load that is observed and all the variable generation. And this forecast is then used to determine which generators will be online the next day. And so the dispatchable online generators will be required to track the forecasted net load and also meet the any differences between the actual observed load and the forecast. And this can be a complicated issue, as these variabilities are very fast-scale variabilities, and generators have to ramp up and down really quickly. Another phenomenon that we see is this duck curve. I'm sure you've all heard of it somehow. And the black line represents the actual load that you see. And all the other levels represent an amount of added solar into to your system. And each layer is 1 gigawatt. So as you add more solar to your system, what you see is that the DAC is essentially getting bigger, and suddenly your dispatchable generators have to ramp up really quickly, or system operators have to bring up a lot of generators online just as the sun is beginning to set and everybody else is going back home and turning every electronic equipment that they have on. As a result of these challenges that are posed by renewables, we find that system operators would usually acquire some reserves to ensure that they meet the net load variability. So load following reserves, think about it as you have a natural gas power plant. It has a maximum power of 500 megawatt. And also has a minimum power of 200 megawatt. It's currently producing electricity at 400 megawatt. This particular natural gas plant can provide you with 100 megawatt of upward load following reserves and 200 megawatt of downward load following reserves. And these reserves can be used to help with the variability in net load. Another quantity that they acquire is ramping reserves. And again, you have your 400 megawatt generating natural gas plant, and it's been scheduled to ramp at 25 megawatt an hour. And this particular plant can give you 25 megawatt an hour of upward ramping capability and 85 megawatt an hour of downward ramping capability. And again, this will be used to deal with the variability in net load. Well, sorry. I cannot get it to switch slides. I'm not sure why. Oh. Cool, thank you. So finally, we have ramping reserves, and they're slightly different. They're slightly different, and they are ramping regulation reserves is more of an automatic feedback response that some generators are capable of providing, and it's basically the ability to move up or down from a set point, in this case 50 megawatt, and regulation reserves tend to be fast-acting and real-time automatic response that quickly tracks load and imbalances in the real time. So given this considerations, we developed the enterprise control simulation methodology, which essentially captures the way the electricity grid is structured, so the physical structure, as well as what ISO New England mimics how ISO New England functions. And as you can see, it comprises of 4 cyber layers of control, where we have your day-ahead resource scheduling, then the same-day resource scheduling, and then a real-time balancing market, and finally a regulation service, and this is built on top of the physical power grid. So Dakota will talk about the data used in the study.
Thanks, Debbie. So naturally, with a large simulator such as the enterprise control, it's going to need a vast amount of data to actually put through the simulation and feed it. And it's this vast amount of data that powers the different scenarios that we will see in the study. But where do these scenarios come from? Well, in developing the scenarios, it's important to know where we're coming from. And that includes identifying trends that we've seen in the changing energy contribution fuel mix that makes up the electric grid. In specific, over the last, say, 17, 19 years, we've seen a major increase in the amount of natural gas used, as well as an increase in the amount of renewables in the system. And so that's part of what led the stakeholders to agree on 12 different scenarios for this study. 6 of them happening in the year 2025, and 6 of them happening in the year 2030. And in particular, for this presentation, we're going to be focusing on 2 of these scenarios, the year 2025 conventional or business as usual scenario, and the year 2030 high variable renewable energy plus or high renewable study scenario. And these kind of bookend the scenarios we see. But one major question that gets asked a lot is what % renewables do we see in these scenarios? But that question is ill-posed because there's really 2 ways we can look at what % renewables we have in the scenario and what the penetration is. We can look at the installed capacity in the scenario, which is seen by the bars on the left, or we can look at the total energy delivered by the renewables, which is seen by the bars on the right. And particularly in the high renewable plus, you can see there's quite a big difference between the 2. So going forward, there's an important disclaimer to make, and that's that these scenarios are neither predictions of the future, nor do they indicate ISO New England's future plans. Rather, they represent 12 consensus scenarios that ISO New England stakeholders have collectively agreed warranted deep investigation. But going back to talking about penetration of renewables, well, we want to integrate them into the system. So from the scenarios, we can know how much renewables we want to integrate in, but where are we integrating them? Right? Because you want to place them where the wind blows and the sun shines in order to get the most use out of them. So using a combination of GIS data, scenario constraints, and clustering algorithms, we're able to cite these renewable resources according to the highest geographic potential. One thing to note is that this actually resulted in a lot of renewables being placed in northern Maine and down and around Rhode Island. But the interesting part about having them up in northern Maine is that resulted in kind of a non-standard generation system where the generation is far up in northern Maine, is far away from major load centers that we would see like down in Boston and including southwest Connecticut. And that poses some issues that we'll get into later on down in the presentation. But to get that power down, that requires transmission. And so here we see the New England transmission system. You'll notice there's not a lot built in up in northern Maine, but then as you work your way south, you have a major load hub in Boston and in southwest Connecticut. It's also worth noting that there are ties into New York, Quebec, and New Brunswick for this system. But this is a fairly sophisticated system, and so the stakeholders agreed to use a pipe and bubble model for this study, where the bubbles represent major load centers. So we can still see Boston is included and southwest Connecticut, the 2 major ones. But then we also have these pipes, which are the interfaces between the bubbles. And that's where you have to obey interface limitations, which is essentially how much power or energy can you transmit between 2 load centers or 2 bubbles, which can potentially pose issues when you're trying to force a lot of renewable power from up in northern Maine all the way down to a load center down in Boston. Now, getting into these load centers, we're also going to need a lot of load data for the simulation. And here we're looking at the 2025 business as usual case. And you can look at load in really 3 different ways. On the very top, we see just load as a function of time. It goes along through a whole year. And in the blue, we see the normal load. And then in the red, as Steffi had mentioned before, that's where the renewables have been subtracted from the load and we get the net load. Then just below that, we have a load duration curve, which is another way of looking at load. And basically the way to understand this is you take all your highest loads and you throw them all the way to the left, and then you take all your lowest loads and you throw them all the way to the right. And you could do that in a sorted order, and you can essentially get a probability distribution where you can see that for less than 10% of the year, we have these really high loads, but then for the entire year, we have a base level of load of at least yay much. And then finally, you can take all your loads, you can sort them into bins, and throw them into a histogram. And one thing that's great at showing is that in the red, we see the net load with the renewable subtracted, and that really shifts the load over to the left. Now, here we're looking at the same thing, except this is 2030 with the high renewable case. And one thing that becomes very interesting is if you look at the load duration curve, you can see this magenta line is at the net zero load. That's where there's zero load on the system. And if you follow that all the way to the right, you can see that the net load actually dips below net zero. And that's where there's not enough demand on the system to meet the generation. If you look just above the magenta line at the green line, that's about 3.5 gigawatts rounded, which is the base level of nuclear generation that we see in this study, where it was assumed by the stakeholders that the nuclear plants would be running 24/7 all year long. So that raises the net zero up, and so that you actually get for about 20 to 15% of the year, you have excess generation. And so that poses some interesting things. And now I'll turn it over to Aram to tell us kind of what we found.
Thank you. Okay, let's get back to the simulations, just some computational information about. This is the general representation of our simulation as Steffi represented. It mimics the ISO New England operations, and it is implemented, the optimization programs are implemented in GAMS, and the passing of information and data between different optimization programs is implemented in MATLAB. And for this study, we run about 1,500 different simulation years with 1 minute time resolution, where each simulation takes about 2 days to complete, and each simulation produces about 500 megawatts of output raw data. All this combined with pre-processing of the data and post-processing, it leads us to several terabytes of data, which means that this is a computationally very heavy study. Now, let's look at some of the results. For example, the dispatch of generation, and see how the demand is distributed between different types of fuels. And this is the 2025 business as usual scenario. And we see that at the bottom of the stack, we have these nuclear power plants. They just produce 100% during the whole time period, and they are not allowed to change their generation output. And on top of that, the orange color is the natural gas, which shows that most of the generation at ISO New England is provided by natural gas power plants. And on top of it, we have various types of renewable energy resources, such as wind and solar. And the interesting part about this, if we look at the magenta color, which is the solar power plants, we see something that Steffi described and called it the duck curve, where we have a dip in the middle of the day because of the generation of the solar plants. And this notion previously was thought as a result of high level of renewable penetration, and this was considered like an exceptional case in California. But nowadays we see that even for business as usual 2025 scenario, we have a duck curve, and this is something that needs to be addressed. Now, moving on to 2030 scenario with much higher levels of renewables, we see that all the effects are just amplified drastically. And again, we have the nuclear power plants running as usual because they are not allowed to be shut down. But we see that the rest of the generation is mainly coming from renewable sources. And the duck curve is actually skewed in a way that it more represents so-called duck dive curve, which is like duck curve on steroids. And this also poses a lot of problems that we'll discuss later on in the simulation. So now we see that while introducing this much renewables into the system is a good way of evolving the power grid in terms of environmental concerns and everything else, but at the same time it brings some technical challenges that need to be addressed. And we're going to look at the performances of different kinds of reserves as Steffi represented, which are the tools that the power system uses to mitigate the imbalances and make sure that the generation meets the demand of the system. And based on the behavior and performance of these reserves, we'll understand what kind of challenges we have in the system. First, let's look at load following reserves. This is the 2025 business as usual scenario. And we see that the blue line is the upward load following reserves and the red line is downward load following reserves. And it again represented by 3 different types of graphs, the time series, the duration curve, and the histogram. But the important takeaway from this graph is that at no point during the year any type of load following reserve hits 0 megawatt value, which means that the system always has enough megawatts of load following reserves to meet the demand and balance the system. Which is good news, because if this is business as usual scenario and supposedly this is the way that the system will evolve unless something changes, the system is prepared to take the planned amount of renewables for 2025. However, when we go to 2030 high renewable energy scenario, we see that oftentimes during the year, both upward and downward load following reserves hit the 0 megawatt value, which means that the system lacks load following reserves to meet the demand and balance the system, which is very bad sign. You shouldn't have that. That's a reliability concern, and it needs to be addressed one way or another, no matter how much it costs. And the reason that this happens is because a lot of renewables integrated into the system, they are replacing the traditional generation units. And as Steffi described, most of load following reserves are provided by these traditional generation units. And now since you don't have their presence in the system doesn't have all these ancillary services coming from traditional units, and they need to be replenished somehow else. So the ISO needs to find a way to procure enough amount of reserves while at the same time continue with integration of renewables. Now going to ramping reserves. So again, 2025 business as usual, we see similar picture that the system is ready. It can accommodate the renewables planned in the business as usual scenario for 2025. And the system operators can just continue doing what they do and not worry about it. But again, going into the high renewable scenario, we see that most of the time the ramping reserves are hitting 0 megawatt value, which means that the system has shortage of ramping reserves. This happens because as we talked about duck curve, we have this steep increase in generation requirement when the duck curve happens. And most of the generation that you have in the system might not be prepared to make that steep ramping up. And also given that most of the traditional units are replaced by renewable units, you have fewer generators with high demand on them, so oftentimes they fail to meet the demand. And this particularly happens, both shortage of load following and ramping reserves happen especially during spring and fall terms where your net load is low and you have less generation, traditional generation in the system. Now the third type and the final type of reserves that we looked at is the regulation. And again, 2025 business as usual case, everything is fine, nothing is getting saturated. The system is ready to take the planned amount of renewables. Now going into 2030 scenario, we see that most of the scenarios, 5 out of 6 scenarios, are having saturated levels of regulation, which means that the system doesn't have enough regulation to balance the system. Only the green line, green and red line, this one, shows no saturation, which means that, again, even for 2030 business as usual scenario, we are able to meet the demand, and the system operators do not really need to change anything in the system. And having all these, the final thing that we need to look at, the performance of the imbalances, how the imbalances are reflected after this. And looking at this graph, we see that as we expected, for the scenarios with high renewables where the system didn't have enough renewable energy, the imbalances are just very high, above 100 megawatts, which is bad. And for business as usual scenarios, they are below 20 megawatts, which are acceptable levels for balancing the system. So again, just to summarize that, these three types of reserves, it shows that the system is able to accommodate some amount of renewables moving forward. But at the same time, if we try to push boundaries, there are other technical challenges that raise up and need addressing. Now moving into, now these are kind of the reliability part of the system, because unless you have balance between supply and demand, your system will just break down. It will not function properly. Now let's look into more efficiency part of integration of renewables and see how the renewables themselves are doing for different scenarios. And one of the ways for looking at this problem is just to look whether the system has congestions or not. And the most important interface that we're looking at is the flow from northern area to southern area. From northern Maine, where, as Dakota described, we have most of our wind generation, to southern area where we have consumption centers. And we see, again, for 5 out of 6 scenarios, we have congestion on this interface, which means that the power produced in northern Maine from wind turbines isn't able to get to the consumption centers in Boston or Southwest Connecticut, except, again, for business as usual scenarios. As we see, for most of the scenarios, we have a problem except for business as usual. I guess that's why it's business as usual. And, and I'll just let Dr. Amro to talk about the curtailment and just wrap it up.
So our final result is really about the curtailment of renewable energy. And best way to think about curtailment is to imagine a wind turbine with a brake on it that sort of slows the amount of generation that wind turbine can have. And what's really interesting is from the 2030 scenarios is that we actually see quite a bit of curtailment for these high renewable cases. So let's start up at the top here. More business as usual, but business as usual in 2030. You see that there isn't very much curtailment. That should not surprise you. If you were to speak to someone from ISO New England today or any of the other ISOs, CAISO, New York ISO, so forth, you'll find that they don't really rely on curtailment as a control lever, a balancing lever, or a reliability lever today. But if we start to advance a lot with renewable energy integration, in the most advanced case here, curtailment becomes really important. It's worth reading here, right at the bottom. That's about 14.5 gigawatts of curtailment. And if you look at sort of the area under the curve, ends up being, in the worst case, it ends up being about 40% of the total energy that could potentially be generated. So that's not a small amount. And I'll come back to that in 2 slides. So there were quite a few findings from this study. The day-ahead market, the unit commitment, or the top layer of our simulation is what commits the different types of generation resources. And these commitment decisions to turn power plants on or off is what drives a lot of the amount of load-following reserves and ramping reserves and regulation reserves. And because it's sort of an on-off decision, it's a very nonlinear and difficult to predict sort of phenomenon. So you always have to sort of keep that in mind. There isn't an immediate correlation between renewable energy and different types of reserves. That said, the simulations that we found in the high renewable cases did exhaust load-following reserves, both in an upward and a downward direction, and we also found the same thing for ramping reserves. Curtailment becomes a very important lever in the future for balancing, and part of that is for balancing, but part of it is also because the transmission system has not been upgraded, so to mitigate the topological limitations of the system. And I mentioned here, again, 14.5 gigawatts in the worst case, and about 41% of the energy of the renewables. There's quite a bit of congestion or limitations by the transmission system, particularly from north to south. We highlight here the Orrington South interface from Maine. And then also we notice that regulation reserves, this automatic feedback response that some generation units have, are going to get saturated. They're going to be used so much more heavily with renewable energy integration. Finally, in the high renewables cases, there is some degradation of the balancing performance. You did see that a couple slides ago. It's difficult to say whether that will lead to reliability events in the future or not. That can be investigated further. But what we basically can say is that in business as usual scenarios, we're doing just fine, and we expect to get kind of what we've always been expecting. But when it comes to the integration of renewables, you can't just expect to put that much energy onto the system and not also make a whole bunch of other changes as well, particularly with market and policy innovations. So what might some of those changes be? And it's important to think about that. One is just the expansion of transmission from remote areas that would have a lot of renewable energy to load centers. Another is to treat curtailment as an actual type of operating reserve. If you're familiar with the mathematics, and you would find that actually the ability to control wind and solar generation in the form of curtailment is a lot like controlling a traditional thermal power plant in many ways. We can procure more regulation reserves from a diversity of energy resources. So traditionally, those regulation reserves might have come from our thermal fleet, but we can also imagine demand response playing an important role with regulation in the future, and that's certainly an active area of research in the literature. We can coordinate the scheduled maintenance of nuclear power plants. So in this study, the stakeholders asked us to simulate that the nuclear power plants would be going flat out for 3.5 gigawatts all year round. But naturally, any type of generation facility has a maintenance schedule, about 6 weeks a year. And you can imagine in those low load periods in the spring or autumn, turning down those plants and giving them the normal maintenance that you're going to have to do anyways, rather than doing it at some other time where it would not be as useful. Finally, we can think about other types of energy resources as well, and we haven't really mentioned in this study, but it's, again, an active area of research, energy storage and demand-side resources. So I would like to thank you all for attending and listening to our presentation. I also wanted to take a moment to thank ISO New England for sponsoring this research and bringing it to Dartmouth. As I mentioned in the beginning, these studies are not done that frequently, and they're usually done by NREL or GE Consulting. So to bring it here to Dartmouth, where we can do a study that's very much germane to our backyard, was really quite incredible. And speaking of which, I also want to thank the project team, Zach, Dakota, Steffi, Armaz, Galen, I think you're up there as well. You guys have been great, and I'm really quite honored to have been working with you on this project. So thank you. I believe we have some time for questions. We wanted to have our audience engaged with our results. Go ahead.
I had a quick question. So in the 2030s scenario, if you were to remove the baseload, some of the results change.
Yeah, I think so. So we were looking at this, and you have here the nuclear generation units going flat out. And one of the recommendations that I mentioned just now is that, here, April, you have a whole bunch of sun, you also have a whole bunch of wind. It would be quite useful to schedule the maintenance of nuclear power generation during these times, at which point in time this duck dive curve might begin to look a lot more like, let's call it a traditional duck curve. It's kind of remarkable to be calling the duck curve a traditional thing. But that might be one way to do it. It's difficult to imagine a future without nuclear generation, particularly as we think about decarbonization and so forth. They certainly have their role within the mix. But it's important to try and think about the collective of energy resources and coordinating them in an effective way so that each one has its role in serving our grid. Yes?
In your simulation, thinking about the reserve, the rapid response reserve, that's traditionally been used for rapid changes in load. Now we're applying it to variable renewable energy resources. But the traditional use is to protect against the failure of something like the largest generator on the network. And did you invade the rapid response reserves in your simulation, or was those sort of set aside as protected?
Yeah. So, the topic of reserves, which is at the heart of this study, is a remarkably complex one. When we talk about renewable energy integration, we focus on what are called normal operating reserves, the load following, ramping, and regulation reserves. Another type of very important reserve is what is called contingency reserves. And contingency reserves are meant to cover when you have a very large power line or power generation facility that, for one reason or another, just out of good engineering prudence, goes out. So you might have, let's say, a nuclear power plant of a gigawatt or so, and it goes out. Then how are you going to respond to that? You would still need to have those types of contingency reserves on the system. That wouldn't really change, but that's not the focus of the study here, and not really the focus of renewable energy integration study methodologies. Please.
I'm excited about the data. I think this is really good information, but I'm really discouraged about curtailing our generation of renewables. Seems like the wrong answer. So I would see how batteries and that sort of storage should be a huge part of the future, especially as they can address the regulation and the ramping up in a very fast response. So is that something that is going to get more attention somewhere?
Yeah. So let me go back here. I'm really glad that you picked up on that. So curtailment is going to become an important control lever, and we need to leave it there. But it's in many ways, let's call it leaving money on the table, right? We can think of that because, first of all, solar and wind don't have a fuel cost. So oftentimes, in terms of the way the markets run, they provide the cheapest operating costs. So that's one benefit. So they'll pull down costs in general. So you don't really want to have curtailment for that reason. Second, if you were a developer of renewable energy, and let's say you were assuming that your wind turbine was going to work 50% of the time, capacity factor of half, then all of a sudden you say, oh, I'm going to lose 40% of that, then the rationalization of that, the cost rationalization or the ROI rationalization for that wind turbine would be much less effective than what you had originally imagined. So that's another issue. And then finally, they don't have any carbon emissions, right? So in operation. So if you have very aggressive targets for carbon abatement, then curtailment is not exactly your friend. But in a sense, all of this is not really a surprise. We had our old grid of dispatchable units serving load. If we bring in a lot of solar, then we're eroding the dispatchability of our grid, and we need to find new control levers. So whether if you don't put on new control levers, then you'll inevitably have to rely on curtailment. The only other place to go is towards the demand side, and I include energy storage within that. So there's a lot of different places where we can think about energy storage and demand-side resources. I have to highlight that there was actually a follow-on study to this one that Steffi led, the New England Energy Water Nexus study, and where we looked at using water resources as basically a form of demand-side management and energy storage, and a very small amount of penetration of, we call them water energy resources, just a couple of percent, can really improve these curtailment numbers. That's certainly not the only way we can look at it. We can look at water, we can look at batteries. People are also beginning to think about hydrogen in the future as well. So it's certainly an area that we want to be thinking about from a market perspective and a policy perspective and a technology perspective to really improve the overall synergies that we find within the grid. Go ahead.
I just wonder, you didn't cover the subject of simultaneous wind and solar loads, which can last 5 to 7 days. So that if you, one of these graphs that you showed, would be applicable, and then your dispatchable reserves that people want to shut down, people want to shut down the gas turbines. And of course, the nuclear plants, none of them are going to be built, but they will eventually shut down by means of their license running out. So that scenario is a real one in New England. No nuclear is a real one. I think that's the one that should be studied. So, 2 items is the lulls, the wind and solar lull, which are very frequent and happen in the summer as well as the winter. And also the fact that you will be without nuclear, that is a certainty within a few decades. That is without a question. So that certainty should be in this study. Can't count on nuclear.
Right. So in terms of the scope of the study, we pretty much had to focus on what the stakeholders asked us to do, right? I think we all know how contracts work, right? There's a scope of work, and you stick to what is being asked. Yeah.
Wind and solar can be zero with days on end. I mean, minimal, zero.
Yeah. The ISO New England perspective, I'm channeling the director of planning. He tends to say things like, "They're all our children," right? And the ISO perspective is to have a balanced point of view towards all energy technologies, and in a study like this, it's important to have that. Personally, I don't know what the future of nuclear is. There are some people who are honestly, very negative towards it for a lot of different reasons. Others that are much more gung-ho. Really, my approach is to be as numerically driven as possible and say, well, if you were to have this particular scenario of nuclear or otherwise or other technologies, what would happen? And I think that's what this study tries to answer. Yeah, Tad.
The countries that are way ahead of us in Amro, Germany, Denmark, Spain, Scotland, how have they handled these kinds of scenarios?
Right. Coming back to the issue of water, right? So the real leader is Denmark. And what a lot of people don't often realize is that Denmark has its aqueous brother, Norway, that has a whole bunch of hydropower and very strong transmission between Norway and Denmark. And so as the Danes integrate a whole bunch of wind, then the variability can sort of be sucked up or dampened out by the Norwegian hydropower. And there are a number of different examples of that across the country, across the world. But in a sense, that's the best case, right? if you happen to have, or you're in a sense blessed with a lot of hydropower, then it gives you a lot of flexibility that that you might not, that you wouldn't be able to do otherwise. And so, I think that's the case of the Danes. Actually, the Spanish have a good amount of hydropower as well across their Iberian Peninsula. So they've done that, and Germany connects a lot with Switzerland. So there's a lot that you can do without hydropower. There's even more that you can do with hydro. Go ahead.
How do your two scenarios treat demand? Do you have the business as usual case and then the high renewable case? Do they both assume the same level of demand?
Yeah, actually close, but no. In the high renewables case, we actually call it high renewables plus. There was also an energy efficiency component that was added to the profile of the demand, and so you actually see that the peak load is just a little bit less than in the business as usual case. But that was the only case that did have a significant amount of energy efficiency component that brought the whole net load curve down.
The aspect that you talk about beneficial electrification both in heating and transportation could potentially drive up demand, and then it also makes you think that there's an economic component of this as well. This tends to argue for real-time pricing to end users to encourage people to shift load off heating and fossil.
Yeah, so these are all really great ideas that we generally support. So let's take your duck curve here. So to emphasize the duck curve, you might want to look at the green outline here. Our high renewables case also had some electric vehicle charging, but the profiles that sort of were given to us as input data was charging in the middle of the night, which is not exactly the best time to be charging, given sort of a duck curve type of shape. If you want to electrify transportation in the most effective way, then we should be supporting charging in the middle of the day when we have a whole bunch of solar power available to us. And in a sense, let's go back to our duck curve shape. Here it is, right? If we could charge our EVs in the belly of the duck curve, that would be really great, right? And that would stabilize the grid in a lot of different ways as well. And the cost of doing so would probably not be that great in terms of consuming the electricity. Obviously, you have to put in charging stations, but you have to do that no matter what. So when you start activating the demand side of the grid, there's a lot more that you could do than you ever thought possible. And it's the sort of the open frontier of our future grid, our modernized grid. It's something that we advocate for a lot. So whether it's traditional demand-side resources that are maybe electrifying heating or electrifying transportation, all of these things can really take our grid to a new generation. Yes, please.
In your simulation, did you use actual history, such as the polar vortex problem we had winter before last, when we almost ran out of fuel?
Yeah, that was that's a really great question. At one point, we, in addition to these scenarios, we were playing with sort of historical data to sort of develop and test the simulator, and compare it to what we kind of know happened. And I believe the data did have the major events like what we call the polar vortices in the popular press, and the simulator did sort of capture what we would expect what we would expect to happen or what we ended up seeing in the past. Yes?
Thanks very much for putting these slides together. Really well thought out. Really excellent.
Thank you.
I had a question about slide 36, which when we turned to that one. That's where you had the imbalances.
Yeah.
Is that, could you look at that slide as a summary of the overall problem?
In many ways, right? So, when we think about a renewable energy integration study, we can be thinking about the economics, which we did not highlight here, partially because there was another study that was done directly by ISO New England, and I'm happy to give you the link for that report as well. And then, of course, the reliability impacts. And the reliability, the main issue here is balancing, and what we see with the let's call it the business as usual operations with non-business as usual energy resources is that there's a challenge there, right? That if we're going to end up bringing on fundamentally different types of energy resources, solar and wind, that we're going to have to adapt to the way our grid operations end up working. And yes, that is reflected in the imbalances here. So it is a call to action to make improvements into how we manage the grid in the future.
Wrong to look at it, though, to say that on a roughly 25 to 30,000 megawatt system, in a high variable energy resources scenario, we're looking at a 100 to 120 megawatt issue.
So, for a little bit of perspective, right? If we were to look at the imbalances on any given day in ISO New England, it would not be uncommon to see excursions of several hundred megawatts, and we might even see up to a gigawatt of an excursion of imbalances, and that excess or under generation would end up being sort of soaked up by New England or soaked up by Quebec, much less so New Brunswick because it's fairly small, but our neighbors as a whole. So, these numbers, if you put them in perspective, are not huge, right? But if you are accustomed to running your grid at sort of this on standard deviations of around 25 or so, and then all of a sudden you're seeing standard deviations of around 80 or 90, a good engineer would say, that's a little bit different than what we had before, and maybe we should be, thinking about how to improve that, right? Yes? Yes, so Hydro-Quebec was in all of the scenarios, and in the 2030 case, they also had like a sort of an incentivized sort of approach where they had the ability to sort of suck up, additional power, given that Hydro-Quebec does have, hydropower quite a bit in the Quebec region. So yes. Yeah, so only lightly so. I mean, if we were very interested in what would be called deep decarbonization, in other words, taking the carbon emissions associated with heating and transportation and shifting them over to the grid, then we would need a completely different set of scenarios than the ones that were agreed upon here. And certainly I would be very interested in looking at those very deeply. Yes?
I think you have talked about the entirely different management technique of the electric grid, which is the rationing and curtailment of consumer use of electric energy. Several countries do this routinely. I used to live in Bolivia. Some evenings, the lights would flicker and go out, and people would go out humble about candlelight. And it didn't do us any harm. Why does it take it as given that electric energy needs to be available to every American whenever he wants it? It doesn't say so in the Constitution. So why
Yeah. So, I think that's a really, really interesting question. So, I'm going to give away my age. I was born in 1978, and that's where was I born? New York City, actually. But I was born in 1978, and that's not too long after the 1973 oil crisis. And in sort of that generation, and also maybe my parents' generation, one of the things that we were oftentimes concerned with is the absence of sufficient energy, the availability of energy, and what are we going to do with that, and then there were all the discussions around peak oil and so forth. That's not our future. Our future is one of a tremendous amount of energy available to us in the form of solar and wind, and they will they will be put onto the grid, and it's going to be a question of managing them. So in that type of future, the word rationing doesn't really jive with that too well, but but the idea of changing your demand patterns in response to, or so that you are taking advantage of when energy is most available is something that we very much agree with. And so I come back to this issue of demand response, right? If there is so much solar in our future and there's so much wind in our future, then we might want to say, hey, maybe I should be running my dishwasher and my oven and scheduling them and so forth, so that they're running in the middle of the day, and I, maybe I'm I only have my graduate student stipend, and I don't want to pay a big electricity bill, and so maybe there are certain times of the day where I know that electricity is going to be cheaper than others, and so I might want to make decisions along those lines. Maybe on my phone, which I can change the settings on my heat pumps to reflect that, so that I only really use energy when I'm an hour out from getting home. I think all of these sort of new generation, active, IT-based Internet of Things, we call it Energy Internet of Things, new book that Steffi has led as well. These are all things that we can be looking at actively, again, to take our grid into a next generation of performance and synergy. Up at the top.
Have you roughed it out quantitatively that demand side management would take care of the imbalances with a very high degree of integration of renewable power generation distributed?
Yeah, so I mean, it depends on the nature of the resource, absolutely. We've published in this area. We've developed algorithms in that area. We've, FERC, the Federal Energy Regulation Commission, has a demand response policy out there. We've compared that in its performance to sort of more new age ones, transactive energy approaches. There is a lot of promise in that direction in balancing renewables. Absolutely. Yeah.
I'm just concerned that ISO New England is going to take this study as just say no, just don't go to renewables. It's too much trouble.
No, I mean, first of all, ISO New England is not the one who is responsible for the integration of solar or wind. Those are individual generation companies that are going to make, well-rationalized, decisions of not just, whether I should integrate one type of energy resource or another, but also where and how to operate it. In no way do I see this as, a cloudy, pardon the pun, future for renewables. It's something that we know that they operate differently than the energy resources, and that we're going to have to make adjustments to take that into account. That is, in my mind, the what engineers are used to doing, right? Continually improving. Here.
I just wanted to kind of follow up on that question. If I understood your demonstration of reserves, film as soon to be a market product, that would allow renewable generators to participate in that market and get paid, I guess,
Well, the suggestion is potentially a radical one, but nevertheless one that I feel that as an academic I can ask. If thermal generation units, let's say natural gas or otherwise, can be incentivized or compensated for providing different types of operating reserves, whether it's load following, ramping, regulation, or otherwise, then there is an equity question of whether solar and wind can do the same. It would take a certain amount of investment to be able to run these solar and wind facilities with the ability to respond and provide those types of reserves. So then why shouldn't they be compensated for providing that capability away from their own self-interest, but towards the balancing of the grid as a common good product? Right? I think that's a really good question that we should be asking from a policy perspective. Yes.
Just a little point about, you said the stakeholders said that the power plants, the nuclear plants have to run flat out all year. And perhaps it would be good if they did their maintenance in the spring and fall. I hope you're aware that that is when they actually do their maintenance. It's called the shoulder season, and that's when they have their outages and their maintenance procedures and their refueling. It just seems like a very odd thing to say, hey, that would be a cool idea when it exists.
Let me qualify what I'm saying. So one thing is what happens now. Another thing is what we were asked to study, and the third thing is what can we do in the future. So you mentioned now. That's right. We have maintenance, particularly in the fall, for in the shoulder season. The fall will not be the shoulder season in the future. The fall will actually be the lowest level, or the spring will also be the lowest level of load. So the difference here is that the reason for doing your maintenance would now change. Instead of being shoulder season, it would be low load conditions.
This low load is also the shoulder season. It's between the two peaks, the summer and the winter peak, and then there's a low load, and that's when you do your maintenance.
Yeah. So, right. So, again, we were asked to put this assumption into our study as, and part of the reason for that was that ISO New England had done sort of a preliminary study with that assumption, and they wanted to make sure that the two studies work together and have comparable assumptions and results. So I'm not disagreeing with you in any way.
You said that the stakeholders had asked you to do it, not actually doing it. Now, to me, from what I see, which is a different place than things, when I hear the word stakeholders, I think equal participants.
Absolutely.
Okay, that's the right thing to think, I believe. So the equal participants committee asked you to do this.
So this entire study was at the request of our NEPOOL stakeholders, and then the ISO New England, of course, contracted us to do it. So all of the requests of the stakeholders were reflected in our contract with ISO New England.
Just one more question, which is off the topic a little bit.
Yeah.
How do you personally feel about the fact that the equal participants committee actually refused to have any media presence at their meetings and have argued the matter up to FERC?
Oh, well, You know, that's a good question. Honestly, I have not given it too much thought, so I'd have to think about it first before answering. Yeah. Yeah. Let me just reflect on it first before I answer. Yeah. Thank you.
Studies seem to show that no matter what's done, there would have to be a lot of building of a lot of different things. Transmission lines, solar power, wind power, other kinds of things. But we seem to be in a situation in New England where no matter what you want to build somewhere, somebody's against it.
Oh, yeah.
And they have
I grew up in New England. I know about NIMBY, right? I'll tell you, the funny thing is, anybody here from Lyme? No? I live in Lyme. And I live on Washburn Hill Road. You know, don't come and like, demonstrate in front of my house or anything. But it's a dirt road, and we built our house there, high performance home and everything. And you go up onto the dirt road, and I was on my way to my soon to be house, and our next door neighbor has one of these sort of yellow, what are they called? Ticket things, right? That says "Stop Northern Pass," right? And I know that's a contentious topic up here in this part of New England, and it's one of the things that makes a democracy great, that we can hash out these topics. But certainly, one of the things that I want to do with a study like this is to say, well, if let's say you're against transmission because you're a superior environmentalist, then you have to recognize that transmission is also serving a purpose and might actually serve a very important purpose in terms of decarbonizing. And so systems level studies allow for us to balance all of these decisions not in isolation, but rather together. And it's one of the reasons why I'm, really enjoy this type of work. Yes.
Like some sort of secret society.
No, we highlighted who they are.
I am sure that among these stakeholders, there are zero people in favor of nuclear, and probably all of them are in favor of wind and solar. So you see where this is going.
I don't think our New England grid is honestly that different from many other places in the country, in that there's a pretty broad set of perspectives when it comes to different types of energy resources. And this study is not meant to advocate one or the other, but rather it's supposed to say, like, answer the question of how do we get them all to all play together well. I'll take one last question, and then maybe we can go out to the Great Hall and speak further offline. Go ahead.
I just wanted to say that the stakeholders, it isn't that casual. What type of stakeholders and what percentage of the votes in the stakeholders meeting is on their website. It's a completely closed site. You just don't know who votes. It's pretty close to it. It's pretty close to it.
Yeah.
It's not just, anybody can become a stakeholder and vote. It's very, very careful.
I'm aware of the representation of stakeholders at our wholesale level. Absolutely. Okay. Thank you, everyone, and thank you again to my students who worked so hard on this.